Okay, hi everybody. So my name is Valentin. Thanks first to the organizers for this incredible, thank you, conference. Okay, so this is a joint work with Pierre Bielawski. And as I think we all come from different mathematical fields, I will start with a quick introduction and motivation also. Okay, we will deal with the other points later in the presentation. So, first observations in classical mechanics, we deal with a space of observables, so things we want to measure. This space is an algebra of smooth functions, defined on symplectic manifold, and so naturally we have a commutativity in the product law between the functions. But at the quantum level, the space of observables is no longer a space of smooth functions. This is an algebra of operators. And so in this case, we have naturally a non-commutative product at the level of this algebra. And so the natural question is, can we link both pictures? Okay, because intuitively we can think that the two are related in some sense. And so you have this idea suggested by several mathematicians that the quantum level can be seen as what they call a deformation of the classical level rather than a change in the nature itself of the observable. So instead of thinking of two separate worlds, we can think that we can connect the two worlds by means of a family of deformation, okay, called star product. I will define it in the next slide. But you see, the idea is to start with the classical pointwise product and then to add something, to deform it in order to give rise to a non-commutative construction. So this is, like I said, the notion of star product. And here I have to stress the fact that this is a formal star product because later I will talk about another type of star product, but first let us define a formal star product on a symplectic manifold. So this is a law you can define on formal power series in a certain deformation parameter, nu here, okay. The coefficients are smooth functions on M. And what's the idea? The idea is to start, like I said, with the classical pointwise product between functions, and then you expand, so you consider an expansion, a series in the formal deformation parameter, so you deform, you twist the classical pointwise product. So you do it in such a way that you keep the geometry. So for instance, at the first order, this is the second condition, you want to keep something related to the Poisson bracket. Okay, so we say that we deform in the direction of the Poisson bracket. And then at higher order, we want bidifferential operators on them. So you see, at the order 0, you have the pointwise product, and then you add some term to deform this pointwise product. Do we have an example of such a construction? Yes, we have. This is a well-known one due to Moyal, so we can consider a flat space, R2n, and that is canonical symplectic form. And then we can write explicitly a formula, okay, which is right here, depending on the symplectic form itself, to define a star product, so deformation of the classical pointwise product on this flat space. Okay, we have an explicit formula. But there is a spectacular fact regarding this star product, and the observation is that if you choose very well the function space on which you will apply your product, then you can make the formula convergent. Okay, what does it mean? It means that you can, after the star multiplication, still get a function, rather than a series expansion, you see? So here you have another formula due to Weil, which is here an integral representation. We call it an integral representation, oscillatory integral representation.
This is due to von Neumann, 1931.
Okay.
Yeah.
And so the proposition is that the space of Schwartz functions endowed with this product becomes an associative algebra. So we go beyond the formal level, you see, and we, by choosing very well the space of functions, we can make the series convergent in order to still keep a genuine function in some sense. And the link between this expression, integral expression, and the Moyal product, you can think about the Moyal product as a Taylor series development of the integral representation. Okay? So this is the notion of a non-formal star product. Okay. So now the question is, can we have this kind of construction in other situations, for instance, in non-flat spaces? And this is the motivation of the work. Okay, so the context is the following one. We will focus on S, the Lie group S, which is the AX plus B Lie group. We have two components, A and L, so we choose this system of coordinates, A and L. We can read the group law on S like this, so L is for left multiplication, okay, so we can write it, and we endow it with the canonical symplectic structure on S. Okay, so we have a symplectic manifold here. And the question is, can we have a star product on this manifold and maybe a non-formal star product on this manifold? An important point, when we talk about star product in this kind of manifold, we want to keep the invariance that we have on the group itself. So we want the star product to be left invariant. So we want that the star product satisfies this relation right here. Okay, so now first ingredient, Rankin Cohen brackets. So the link between Rankin Cohen brackets and deformation quantization is not straightforward, but long story short, I will try to give you the main steps of the construction. So it starts with modular form. Okay, so a modular form is a holomorphic function satisfying a certain invariance property. Okay, it turns out that this is important in number theory, for instance, but the problem with such modular form is that it's hard to transform it in order to still keep a modular form. Okay, so for instance, when you derive such a form, you don't get a modular form again. And so the question solved by Rankin and Cohen is, what is the set of operators so that when you combine two modular forms, you still get a modular form? And the answer provided by Rankin and Cohen is this notion of Rankin-Cohen brackets, okay, indexed by n here. And you have this expression. So the way you can combine two modular forms in order to still get another modular form. Okay? So then you have another observation due to these three mathematicians. And I can summarize this observation as a slogan. If you sum Rankin-Cohen brackets, you can define a deformation quantization on the algebra of the modular forms. Okay, so this is the formula. You see, by summing Rankin-Cohen brackets and by introducing a deformation parameter, you deform the algebra of modular form. But you can go a little bit further. Cohen and Moscovici notice that you can, in fact, extend this construction to define a universal deformation formula. So what does it mean? It means that you build a machinery allowing to deform other type of algebras. Okay? That's it. Okay, so now the idea is to use this machinery on the context of the Lie group S. So we apply the machinery of Cohen and Moscovici on the universal enveloping algebra of S, and it leads to a formal star product, star RC for Rankin-Cohen, on the Lie group S. Okay. It turns out, after a geometric construction, that this product is somehow related to the Moyal product, but not the classical one, a restriction of the Moyal product. And so here you have a construction based on Rankin-Cohen brackets in order to have a star product on S, and this star product is related to a restriction of the Moyal product. this product is, star product, sorry, is also left invariant, and so we can wonder, is it possible, like in the case of Moyal in the flat space, is it possible to give rise to a non-formal expression for this product? This is really the main topic of the work. But you see, this is not easy because for the moment we have, let's say, the expansion, and we look for the functions, the integral representation, such that the Taylor expansion of this give rise to the formal Rankin Cohen star product. So the question is not straightforward, and so we need, let's say, inspiration. And we will get inspiration from another star product on S. So this is a particular example of the construction due to Bielawski and Guéral. And if we apply their construction on S, we get a left invariant star product. So what is the main steps of the construction? And you can take a look at their book if you are interested in. But the main ingredient, and it's important to define it for the rest of the presentation, the idea is to find what we call an equivalence or an intertwiner, and that's the same, that will change one star product, namely here the Moyal one, but remember Moyal is adapted to the flat case, not for S, and the idea is to start with the Moyal product, which is not S left invariant, and then to modify it by means of an operator called an equivalence in order to give rise to the right left invariance. So this is the definition of an equivalence, and what is important is, you see, the third condition means that this equivalence allows us to intertwine two star products. You see, so the idea is to change, to twist one of the product to give rise to the other one. So we have this intertwiner relation in the third condition, and so now we look for a particular expression for T to get the left invariance of the star product on S. So this is the idea of Bielawski and Guéral, and you have here the formula. You don't have to keep that in mind. Don't worry, there is no exam at the end of this talk. But you get an expression, okay, for a star product, Bj, for Bielawski-Guéral, which is left invariant. And remember, we start with Moyal, we twist it with an equivalence, and then it gives rise to a left invariant star product. But on the top of that, as it was the case for Moyal, it turns out that if you choose very well one particular space of functions, then it gives rise to a non-formal star product. So here again, for the construction of Bielawski and Guéral, if you consider a Schwartz space type functions, okay, related to the geometry of S, then boom, you get this expression. Okay, once again, this is an integral representation, and it means that the Bielawski-Guéral star product becomes non-formal. Okay, so you have an algebra, an associative algebra, sorry, so SBJ endowed with the star product Bj, so Bielawski-Guéral. All right, so to sum up, for the moment, what do we have? We have on S two star products, two formal star products, Bielawski-Guéral and Rankin Cohen. For Bielawski-Guéral, we have a non-formal equivalent, and we wonder, is it possible to have the same kind of construction for Rankin Cohen? So what's the idea? What is missing in the picture? We miss the potential relation between Bielawski-Guéral and Rankin Cohen, you see? So question, can we link the two in order to use the construction of Bielawski-Guéral to give rise to a non-formal Rankin Cohen star product? That's the question. So first question, can we link, is it possible to link the two formal star products? And we have a very interesting geometrical result here saying that yes, due to second-order cohomology argument, yes, it's possible to link the two formal star products by means of an equivalence. Okay, so this is an existence result. So that's very interesting because it means that it makes sense to look for an expression, but unfortunately we don't have this expression. So we have to find the expression of the equivalencies between Bielawski-Gerald and Rankin Cohen. All right, so that's what we will do right now. Okay, so for that, we will use what we call a retract method. So just for your information, there is a dedicated paper on this subject in the preceding volume 1, I think. So you can take a look at the construction in general. And here we apply this methodology, let's say, to the case of Rankin Cohen. But roughly speaking, once again, the idea is to use, like I said, an equivalence to transform one star product into another. And basically here, we know that for the Rankin Cohen construction, we have a certain invariance. You can look at this invariance at the level of algebra. And instead of focusing on T itself, the equivalence itself, you can define a map D, okay, the bottom of the slide, in order to give rise to an algebra morphism between the algebra of invariance you want and the algebra of derivation of the star product. So you have to pay attention to what kind of, so what is the sense of the map and things like that. But the idea is to make use of this algebra morphism to enforce the invariance you want. Okay? And if you write explicitly the conditions to get an algebra morphism, it boils down to a system of PDEs, of distributional PDEs. And if you have enough time, and if you are sufficiently crazy, you can try to solve these equations. Okay? And after a while, you get expression. Okay? And here you can see an expression representing all the possible equivalencies we can get between the Bielawski-Gerald star product and the Rankin Cohen star product. Okay? So now we get the link, formally at least, between Rankin Cohen and Bielawski-Gerald. And now, to end the story, we will transport the construction, the non-formal construction of Bielawski-Gerald by means of this equivalence. Of course, we have to make sure that everything makes sense, so we have to use to study in an analytical viewpoint all the construction, but we will basically transport the construction of Bielawski-Gerald in the case of Rankin Cohen. And so, okay, so this is not very important, but now, like I said, we transport the algebra of Bielawski-Gerald. We can study analytically what we get as a function, and by transporting the star product itself, we get the main result of the work, namely the fact that we can define an adapted space, okay, which is of the type, a sort of a Gelfand-Cheloff space. Okay, you have more details in the paper if you are interested in it. But we have an associate, let's say, a well-defined space of functions on which you can apply this formula, this integral representation, okay, in order to give rise to an associative algebra. Okay, and what is the relation between this integral representation and the Rankin Cohen construction at the beginning is that if you consider a Taylor series of this expansion, you get precisely the Rankin Cohen deformation defined at the beginning of the slide. So that's why we decided to call it the non-formal version of Rankin Cohen star product. That's it for me. Thank you for your attention. You have some references.
Thank you very much. Are there questions or comments? I see Paolo.
No, you use the affine group, no?
Yes.
So since for the affine group, you have square integrable representation, no? And so you can construct a covariant star product for the affine group. I was wondering whether there is some relationships with the product that you consider here.
It's a good question.
Because in that case, it will mean that your product is essentially a product of operators, and that's why
no.
So in fact, the difference is the equivariance group. So as you have the modular forms that are, you know, SL2Z. Well, in this yeah, the Rankin Cohen brackets are SL2 invariant, SL2L invariant. If you construct the product you mentioned with the unitary representation of the AX plus B group, then you don't have this invariance, and so this somehow you have no relation with analytic number theory if you construct just the AX plus B thing, and the whole point here is that you get it.
The other side of what you said, the star product, of course, is the original one is invariant under the whole symplectic group, and I think the AX plus B group is inside, isn't it, or no? Is that the original invariance of the original star product? Does it have a?
Yeah.
Yes.
So if that's true, I'm not sure if the AX is in. So if it is, then you could look for already have an invariant star product onto that. And you could restrict, which is basically what you have done. You restricted your star product to preserve that invariance and have by a representation. I think you can make it invariant as well. So it might be the same.
Okay. Okay. I see.
But a very interesting calculation, by the way.
Okay. Okay. Thanks. Thanks. Okay. I see.
Just a comment to your question, and you are completely right. But the thing is, if you do that just like this, just by restricting to the orbit of AX plus B on the plane eventually, if you do that, you see, the point is always that you have a strong relation with analytic number theory, so with the algebra of modular forms. And for that, if you think about the algebra of modular form, what is a modular form? A modular form is a holomorphic function that is fixed by an arithmetic group like SL2Z, for example, under the Mobius transformation multiplied by something. The Mobius transformation is not a linear transformation. So this is not this restriction. In other words, if you want to think about it as a geometrical question, if you restrict to the plane, you're dealing with flat geometry. But you don't have this relation with the Rankin Cohen brackets, because if you want a relation with the Rankin Cohen brackets and the modular forms, you need to work with the hyperbolic geometry. So that's the whole point. The curvature is not zero in this case. Is there another comment or question?
Sorry, maybe can you go back to the explicit form of the product? Maybe you can illustrate, even if there is no exam, but we can you say something about that? I mean, to gain some insight from
about the formula right here.
Yeah.
Yeah. So, I'm not sure what kind of information you want, but we get, you see, the same kind of structure of the expression than in the case of Bielewski and Gall. We have this oscillatory integral here, and so thanks to this formula, we obtain also an associated space of functions that is very particular. Like I said, this is related to Gelfand-Schilov spaces. So you have a condition on the support of the Fourier transform on the functions, and you have like a condition on the support related to a strip that will disappear as soon as you let the deformation parameter tends to 0. So you have like a nice observation at this point. And a surprising fact, this is not in the paper, but you can get the same expression using the observation mentioned at the beginning of the presentation about the fact that this Rankin Cohen star product is a restriction, is a Moyal product, but restricted on the upper half plane. Okay, and you can connect the two constructions. Unfortunately, this is not in the paper, but maybe we have to write it as a second part. But this is everything is connected here.
One geometrical comment about your question is that the phase here that you see, this K1 square, blah blah, actually this is the flux of the symplectic structure through some kind of triangle in the space. Yeah, so that is so this is really quantum mechanics. I think we should thank you very much, Valentin.